All right, everybody, I'm going to give you a few more examples of using Green's theorem. And just as a reminder, I wrote a few different versions of it down here, ones that I'm assuming that you're familiar with. All right, so it'll make the process go a little bit faster. And just as a reminder, if a vector field is given like this, we said for C, is given by the vector value function R of t, then we showed in a previous lecture that all three of these integrands, they represent work now, right? We imagine that an object is moving along the curve C under the influence of some force field, okay? So we showed in a previous video that these three integrands are all equivalent to each other. And we also said that if the curve C is a closed curve, then this particular version of the work interval is referred to often as circulation, okay? And we also refer to this one. This is a tangential component of the force field, right? The normal component of the force field is given by this vector. We call this the flux integral. And again, we talked about these things in other videos. All right. Here is a reminder of Green's theorem. I call this the regular form of Green's theorem, right? The regular form of Green's theorem, that was this right here. Of course, we know that again, I just mentioned it. This integral right here is equivalent to these two. We also showed that the circulation form of Green's theorem could be also written as the cross product of a vector field F dotted with K, where del cross F dotted with K is equal to this expression, partial G with respect to X minus the partial of F with respect to Y, which of course we see right here. In a similar way, the flux form of Green's theorem, we showed in a previous video, was equal to this expression. We call this the divergence of the vector field, or the partial of F with respect to X plus the partial of G with respect to Y. So we actually have three different versions of Green's theorem. I call it the regular form, the circulation form, and the flux form. Okay? All right, so let's use that just to do just a handful of examples, all right? Let's suppose, okay, we want to evaluate the line integral. Okay? And let's say that the curve C is the triangle shown. And let's say it's positively oriented and the region is shaded. Okay. All right. Well, if I apply Green's theorem to this, then I can replace that integral with this one. Okay. Now, again, my vector field, you see it right here, right? So this is my F, and this is my G. Okay. Well, by Green's theorem, and I'm just using the regular form, take the partial of G with respect to X, and then subtract the partial of F with respect to Y. Okay. And that's going to give us, let's see, that'd be what, 1 minus the cosine of Y? Okay. Now evaluate my integral. Now I need my boundaries over here, gang. I need to figure out those, and I need to figure out my limits of integration. So it looks like we're going to have, let's see, if I integrate with respect to Y first, maybe I set my integral up like this. Let's see, it looks like our limits of integration with respect to Y and then X. Okay, that arrow is going to pierce the region along the boundary, which is the x-axis, y equals 0, and it will leave the boundary, which is the identity function, y equals x. And that arrow can go from left to right without leaving the region from 0 to pi over 2. Okay. And after that, it's just straightforward integration. I'll leave those details to you to fill in. And I'll just tell you that the result should be pi squared over 8. Looks like -1. Okay. Now you verify that. Don't take my word for it. You verify that. Okay. All right. Our next example, we want to evaluate the line integral. And once again, our curve C, it's going to wind up being a triangle again. So we're going to go from 0, but this time 0 to 1. Again, we'll assume counterclockwise rotation and our region, which is bounded here. Okay. So I'm going to make a note here. My vector field has those components. Again, I'm getting those directly from the line integral itself, right? My line integral is the differential form of the line integral. Okay, in other words, let me show you, just as a reminder, right? This one right here. Okay. All right. So let's see. If I apply Green's theorem to this, we'll take the partial of g with respect to x minus the partial of f, which is this fraction right here, with respect to y. Okay, now of course the first derivative is going to be 0. The second one, by the quotient rule, like that. Okay. All right, let's see. Now we'll set this up again using my region right over here. Let's integrate with respect to y first. We're going to get y equals 0 again to y equals the identity function. X is going to range from 0 to 1. Okay. And once again, this is just like the first example. It's going to be a straightforward integration. Okay. Maybe this one will do a little bit more. We integrate with respect to y first. This is a chain rule. Oops, that should be dx. Sorry about that. Okay. Looks like we're going to wind up with -1 over 1 plus x squared plus 1. Okay. And when we integrate that, it looks like we'll get inverse tangent of x plus x from 0 to 1. To get -pi/4 plus 1. Okay? All right. Next example. I want to evaluate this line integral. And our curve C is the unit circle. Okay? Again, notice it's actually written a little out of order. I'm going to rewrite it like this. I'm sorry, this should be a dx. Oh, I did that again, didn't I? Okay. Now I want to show you something. I want to compare this, right? Compare this integral to this one. You recognize this one? Yeah, that's the flux form of a line integral, right? That's actually this. Okay. So that means to apply Green's theorem to this, I'm going to use the flux form of Green's theorem. Okay. Okay. So to use that, right, flux form of Green's theorem is this. So here is F, and this right here, that's my G. Okay. So the partial of F with respect to X is 2. And the partial of G with respect to Y is 4. And I can move that constant through the integral symbol. And that's going to give me 6 times the area of the region. But the region is a circle whose radius is 1. So the area of the circle is just pi. And so we get 6 pi. Okay. Alternatively, I could have written like this. All right, go back here. Gang, actually distribute the minus sign through. Okay. And then at this point, think to yourself, the vector field is now this. Okay. Then apply the regular form of Green's theorem. Okay. So in this case, this would be my F. This would be my G. And the partial of G with respect to X is 2, minus the partial of F with respect to Y, which is -4, which once again is 6. And 6 times the area of the region, once again, we get 6 pi. Okay. Always love those kind of integrals where you don't have to do any work. Always remember, what's the best integral? That's right, the one you don't have to integrate. All right, till next time.